Okay, welcome to the first video in our second section. This is on limits. Before we get going on limits, maybe just a couple of general thoughts. In preparation for this course, one of the things that I did is emailed one of my old university professors, asking him just for some feedback on some of the things that students struggle with or that students are good at, and two things popped actually from that email. Actually, three, but only two of them matter to you right now. One of the things that I learned is that he said the failure rate for kids either failing first year calc or dropping out nationally, like across Canada, is 50%. Like 1 in 2 kids will either drop the course because halfway through they decide they don't want to do it anymore, or will outright fail it. And that was shocking to me. I was like, oh my goodness, that's so high. Which I think to some degree lends a lot of reasoning to why I want to try to structure this course the way I do, to try to prepare you as best I can for the rigors of university, because it's definitely a different system there. It takes a while to figure out. So that was one thing I learned. But applicable to this unit, he mentioned that one of the things that students do not enjoy, not so much that they didn't necessarily do well on, but that they did not enjoy, was limits. So I want to forewarn you that most students, and I'd agree with this too, limits are not necessarily the most enjoyable topic. It's a different way of approaching things. It has a different type of notation as well. It actually makes it very challenging to email. Like when we do want to email to communicate, it's going to be hard because you can't really type in limit notation all that well. So that's one of the challenges. The third one, by the way, in case you're wondering, was that the thing that kids struggle the most with is something called the chain rule, which we're doing in our next section. So when we get to chain rule, I'll point out like star this thing, because my old university professor said that that chain rule is the one most critical skill kids need. So, okay, let's get started on limits. I want to actually begin, because I don't think I have it in the notes here anymore. Just got to scroll through. No, I don't. I want to begin with what was known as, I think it was Zeno's paradox. It's a story, basically, that a guy made. It's actually like a thought problem, if you've ever heard of these before, where it's mostly just hypothetical. And the idea is that imagine that you want to like walk to the wall, right? So I'm just going to draw a picture here. Imagine that this is you. And imagine that there is a wall over here. This was the guy's paradox. Big wall over here. Big Donald Trump wall, I guess. And what we want you to do is we want you to walk halfway there. And so let's say you walk halfway there. So you've walked, and let's say that about halfway takes you to here. And then he says, okay, now that you've stopped, let's walk another halfway there. So we'll go another halfway, and now you're about here. Right? And in terms of the distance that you'd covered, hopefully you'd agree that at first you covered 50% of the distance, and now your running total is you're up to 75%, right? Because the next half means you added like an extra 25%. But then his paradox basically says, well, let's just keep doing halves at a time. So if I go halfway there, and we get to this point right here. And if I go halfway again, we get to this point right here. And if I keep going half over and over and over again, this paradox, I want to think it was Zeno or something like that. Can't remember his name off the top of my head. His paradox basically stated that you'll never actually get there, right? If you go half and half and half, that will never work. And we actually already know this from a topic in Math 30-1. This is essentially like a graph of an exponential function, where as you keep going, if you keep going half and half and half and half, this is like the graph of 1/2 to the power of x. Now, will 1/2 to the power of x ever equal 0? And the truth is that it never will actually equal 0. This graph will never keep getting cut in half. It will never touch the axis, right? Because even if you do 1/2 to the power of 100, it still is not 0. It might be 0.000001, like something really small, but it never officially equals 0. And this is the basis of what we consider to be limits. We use the word limit then to describe the fact that this thing right here, although it does not actually exist, we would use this notation. And I'm kind of going ahead of my notes here. This is the limit as x approaches infinity, if you guys know that symbol, for 1/2 to the power of x. We would say actually it is equal to 0. So here's how this notation works. This is the notation, and this is why kids don't overly love limits, because it's awkward and it's not familiar, and we only use it for a little while. But the idea is, let's say that x keeps getting bigger and bigger and bigger, and it keeps getting so big that it becomes infinity. You know the symbol for infinity? So like x right here is so large that it's like a largest number. Now, does it actually equal 0 on its own? Well, it does not. But the limit notation means that it's getting super, super close to 0. So we may as well say that it's effectively 0. And that's what a limit does. It says, what is it effectively becoming, even if it doesn't quite get there? Kind of like with my wall example, right? Even though you're not officially ever going to be at the wall because you're only getting halfway and halfway and halfway, and you might be millimeters away, effectively you've reached it. So that's what a limit is. Right? And that's where my first slide goes here. Imagine you've got an infinite geometric sequence where you start with 1/2, 1/4, 1/8, 1/16, where essentially what you're doing is you're doing 1/2 to the n. You're doing an exponential decay graph, right? As n approaches infinity, the terms do become closer and closer to 0. They become closer to nothing. But, I mean, in terms of them being closer and closer to nothing, they don't actually reach 0, so hence the limit notation. Right? So this is what I just showed you on the previous slide that I just kind of did freehand. This is the notation we'll use. The limit, so the idea is that what is it getting closer and closer to? What is it limiting out at? As 1/2 goes to the power of n, or x, or whatever variable you use, as long as this keeps going upwards and upwards to infinity, as it gets bigger and bigger, your graph will keep getting smaller and smaller, and it limits out to the point where it's basically 0. And this is kind of similar to the like an asymptote, if you know that term, asymptote, on like a function graph. It's kind of the same concept, only we're going to build on it and use it in more scenarios. So let me read through some of my notes here. The limit then is how a function behaves near a point being considered. But we don't actually care about the point itself, right? Is it actually possible for you to plug in the number of infinity into your calculator? Well, no, it doesn't really work. It's more of like a theoretical concept. We're actually going to not just study limits as something approaches infinity, but what happens when x gets close to 1 or when x gets close to 2. And when we use the limit notation, we don't actually care what happens when x is 1 or when x is 2. We just care about what happens when it's close or when it's near to that point. So in terms of like terminology, this is, again, why kids probably don't like limits all that much. It's a lot of jargon. Like you need to know the math speak. So the limit is what the function, the graph looks like. It's what the y value looks like it's going to do, though. Where is it getting close to at the point a, f of a? Let me give you an example here. Let's say you have a graph, and it looks like this, but then there's one of those like holes in the graph. You know, one of these graphs where it might be like, say, x plus 2, x plus 3, over x plus 3, one of those kind of graphs where technically it ends up canceling, but it causes a hole. Well, if I ask you what is the value at this point, you actually can't answer it because there is no value. But we might ask you, well, what is the limit as x gets really close to this unknown a value point, right? And so that's what this L I put in this notation here is. I mean, that's the limit. It's a number of some type. So in order to figure out the limit, then you got to consider what happens on the right and left-hand sides. If the right-hand direction is getting close and the left-hand direction is getting close, and they're getting close to the same number, there's actually some math properties regarding that. But look at this here. Is there actually a point right here when x is 2? And I'd say, no, there's not. But what I could say is that the limit as x approaches 2 for our function, I could say it's getting close to 4. Now, is f of 2 equal to 4? I'd say no, it's not. If you try to plug in 2, 2 does not exist. There's no value for 2. So 2 does not actually work. If I tried to go to your calculator and go to that like value thing, where you go value when x is 2, it would give you an error. But hopefully you get where we're going with this. As x gets close to 2, as it gets near or close, see how it basically is, it's approaching 4, but from the left hand and the right hand side. So you have to consider both sides, because maybe one side goes to here and the other side goes down to there. And we'll do some examples on that here. So let's try one. Here's a graph, x squared minus x minus 6. And we want to find the left and right hand limits as it approaches 4. So to deal with this, I'm just going to sketch a quick graph. And hopefully you guys can do this just kind of in your heads a little bit. if I wanted to sketch this graph, the first thing I would do, oh, by the way, I want you to do this in your head. I don't want you to use a graphing calculator as much as possible. Like, only use it in case of emergency. Because, again, one of my goals is to prep you guys for first year university. You're not going to be allowed to use a graphing calculator. One of the course outlines I found specifically says, like, they want you to buy just a $15 basic calculator, so that you can handle doing, long division and stuff like that, but it doesn't want you to graph. That defeats the point of this. So start practicing graphing just using your knowledge and intuition. So if I wanted to do that here, the first thing I would plot is I know where the y-intercept is. It's a -6, right, due to the constant term. And then the other thing I would do is I would know that this is actually equal to x minus 3 and x plus 2 due to factoring, and that gives me my intercepts. One of my intercepts is at 3. And the other intercept is at -2. And that's enough. That's enough to get me kind of the rough shape of the graph, at least right now. We actually have a whole section on curve sketching, but this should do for now. So what I'm asking you now is what happens as it approaches 4, right? So as it approaches 4, 4 would be right here, somewhere along those lines. Now, I can, in this example here, figure out what actually happens when it is 4. So if I do f of 4 and plug in 4, 4 squared minus 4 minus 6 will give you 16 minus 4 minus 6. That should give you 6, right? So the point 4, 6 does exist on the graph. As it approaches from the left, which would be this way, as the graph kind of...
Kevin Cleaver, please call 3500.
If you imagine like a dot kind of plotting it as it comes around this way, as it comes this way, what is happening as it gets close to x being 4? Well, the limit as x approaches 4, here's how the notation works. We put a little negative up in the corner. This means that as you approach 4 from the lower side for this function, it is indeed getting closer to 6, which makes sense because the value there was 6. As it approaches from the positive side, the same thing happened. The limit as when x approached 4 from the positive side for our function, it was also 6. So in this case here, the number actually existed, like 4 actually worked. There was a value there. And the limits from both sides worked. So I know it seems kind of silly at first, and maybe this is why kids get frustrated with limits, because it seems so dumb, right? But I mean, hopefully this example back here kind of shows you that right here, if I asked you for what f of 2 is, you actually can't plug 2 into whatever this graph is. There is literally a hole there. But on this one here, we actually could plug it in as 6, and as we approach from one side to the other, it works. And here's one more test. What if I were to plug in the number, like, say, 4.0001, just slightly bigger than 4? How would that look? So if you did 4.000001 squared minus 4.0001 minus 6, what would that get you? So here's my graphing calculator if you can see it. Hopefully that mostly shows up on the screen I've got here. If I take, now again, this is the kind of calculator that you can use. I don't want you to go to y equals and graph something. But I mean, doing a calculation here, like 4.001, like this would be valid. Like a professor would allow you to use a calculator that could do this. What does this equal? Well, okay, it equals essentially 6, right? It's not exactly 6 because it's slightly more, but isn't it getting closer and closer to 6? If I tried 4.0001 and made it an even closer to 4 value, let's make sure I use the right number of zeros. 1, 2, 3, 4, 5 zeros. Well, now it's even closer and closer to 6. There's only just a little bit of variance off, right? So that's one way that we can check. This right here then would be the limit as x approached 4, but from the positive side, meaning that we made our function be just slightly bigger than 4. We now have some empirical proof that it's equal to 6. So that's actually all there is to this example here. Just tell me what the limit is. So the left-hand limit is where you do the negative sign, and it was equal to 6. And the right-hand limit, which is where you put the little positive sign, it was also equal to 6. Now, for notation, we could use the actual equation right here, or we could abbreviate it with just f of x, which is just a fancy way of saying the function you're using, right? So both would be valid, just depends on how much detail you want to give. Okay. So here's our first definition then. A limit then only exists if the right and left-hand limits exist. If the left-hand limit gives you 5 and the right-hand limit gives you 5, then the limit exists. And maybe many of you have heard that quote out of like the Mean Girls movie, I think it is. People always laugh when I get to this section because if they've seen the movie, the limit does not exist or the limit does exist. That's actually kind of where we're going here, is to figure out, does the limit exist or does it not? And so on this previous example right here, because the right-hand limit was 6 and the left-hand limit was 6, the limit does actually exist. Let me show you an example where a limit would not exist, because a lot of kids will ask that question like, well, how could this not work? What if we had a function that looked like this, where you had a function that went up like this, and then it started again over here? Well, as we approach from this side right here, let's say it's getting closer, the limit, as x approaches, let's say 2 from the negative side, this might have been giving you 3. But here, the limit, as x approaches 2 from the positive side, as you go this way here, it's actually like -4. Well, since these two things are not equal to each other, we would say the limit does not exist. So there are scenarios where there is no such thing as a limit. So here's some vocabulary, some reading to go along with it. So many limits can be found by just substituting the value of x in. If I just say, well, what's the limit when x approaches 3, then just plug in f of 3 and see what you get you. That can work. And that works for continuous functions. And hopefully you guys kind of know what a continuous function means. I think we used this vocabulary already in a video. A continuous function is where it just keeps going from left to right. There's no gaps in it. So a continuous function has no asymptotes, no points of discontinuity. Informally, it means you can keep drawing the graph without lifting a pencil, right? So here is a continuous function, right? Like I didn't lift my pencil off the paper. But here, if I draw on an asymptote, there's an asymptote here. Well, no, now I had to lift my pencil off the paper. That's not continuous. There's a gap, right? Or on this graph here, if I were to do this, put a hole in the graph, and then kind of keep going, that's not continuous either, right? So back here. Informally, if you can draw the graph without lifting a pencil, it's continuous. And then the graph can be continuous over some intervals, but discontinuous over others. So you can have a section here where for here to here, it's continuous, but then there's kind of a spot where it's not. You can even have a graph, for example, where it does this, down to there. And then there's a nice big gap, and then it restarts again. So like from here to here, it's continuous. From here to here, it's continuous, but there's like a big hole in the middle. And hopefully you know some functions like this. For example, if I were to ask you for x squared minus 4 square rooted, so that was your function. This is something you should have done in Math 30-1. An x squared minus 4 graph normally would look like this. It's a quadratic like this. But then when I ask you to square root this graph, hopefully you've seen this before, it creates a graph that does this. And there's a huge gap right here in the middle where like literally the graph does not exist through this whole middle section. And the reason why is that, see how the graph was below the axis here? These are negative values. And if I ask you to square root a negative value, you can't. And so the graph doesn't exist in the middle here. So this would be a graph where there's a huge gap of discontinuity. Okay, so here is a better definition, though, of then being continuous. A graph is then continuous, not if you can't just lift your pencil, but if these three conditions exist. So first of all, the function exists for every x value on there, where x is a. So like if I tell you that x is 2 or 3 or 4, there's a value for it. There's no error. Like if you go to your table of values and I say, what if x is 1? You say x is 3. Perfect. X is 2. You tell me x is 4. Awesome. If x is 3 and you tell me that it doesn't work because there's like an error, well, then it's not continuous. Like literally every single number needs to have an output value. 1, 2, 3, 2.01, pi, -2, a million. Every single input better have an output. If it doesn't, it's not continuous. That's the first requirement. Okay. Now, the second thing is that there also better be a limit as well. So what that means is that as it approaches from this side and as it approaches from this side, there better be a limit as well, where they both limit onto the same number. And then the third thing is that whatever the value itself is and whatever the limit is, they better actually be the same as each other. Again, some kids, they get confused by this and they wonder, well, how could this not be continuous? Let me show you an example. Let's say we had a graph that did this. Like that. Let's say this is your graph. Okay. Does every value of x seem to exist along the domain? I'd say, yeah, like -5 is over here. There's a value there. -2, there's a value here. 17/2, yeah, there's a value there. Pi, there's a value there. Right? All those seem to have values. Now, right here at, like, say, 2, is there a value? Well, there's a hole in the graph right here, but hey, way down here, that value does work. What about 2.01? Yeah, look, there's a value. It's right next to it there, or 1.999. It's got a value right there. So every x value along the domain works. That's the first condition. Is f of a always defined? That works. Right? It's even defined down here. But look at the limit. Is there a limit? Yeah, there is too. Look, both this side and this side right here seem to hone in on the same number. But even though the limit exists, both sides are honing in on the same number, and the value exists, the value itself is not the number they're honing in on, because essentially it's getting closer and closer and closer here, then it hops down there, and then it restarts up here again. So this would not be continuous. And you guys should have known this wasn't continuous, because look at how I draw it. I draw it, I then lift my pen off the paper, draw the dot down here, lift it back up, and start again. So, I mean, that's, again, a reason why it's not continuous. But this is now the mathematical definition of continuity. So here's your steps. First thing you want to do, sketch the graph, make a table of values. Find the limit from the left-hand side, find the limit from the right-hand side, figure out whether there actually is a limit, state whether it does, and maybe to put step 5 in, make sure that your table of values number is the same as your limit, and see whether it's continuous. So let's try an example. Find me the limit as x is approaching 3 for this particular function right here. So, I mean, first thing we should do, let's sketch a graph, make a table of values. We can work on that, or let's just make just one table of values. Let's just deal with 3 for right now. What happens if I plug in 3? What is f of 3? Well, it's 2 times 3 squared minus 4 times 3. So that'll be 9, 18 minus 12, it's 6. Right? So if we were to have our graph of whatever this looks like, I'm just sketching a rough graph, if you plug in 3, it gets you 6. Awesome. But now we want to check to see what happens if we try a number just slightly more than 3, like say 3.001. Let's try it. Move that over here. 2 times 3.001 squared minus 4 times 3.001. This is me testing the limit on the positive side, slightly more. Yeah, look, it's about 6. So I could say the limit as x approaches 3 from the positive side for my function was 6. I mean, technically it was 6 point something there, but effectively it's 6, right? And if I try it from the 2.99 side, I try it from the negative side, where it's slightly less, it should also basically give you 6, right? 2 times 2.999 squared minus 4 times 2.999. One more 9 to do it properly. 5.99, but isn't that getting really close to 6? So what is the limit? The limit is 6. Okay, let's try some different examples, though, because you might be thinking to yourself, man, this is stupid. Like, why are we doing this? And, I mean, yeah, for those first examples on basic polynomial graphs, polynomials are continuous. There's nothing special about them. But let's talk about this one here. What about if we do a function here where this is a reciprocal, like a rational graph? Right? If you know what this graph looks like, hopefully you have some awareness about how this is going to look. This is going to have an asymptote at 2. And then it should look something like this. Now, as x approaches 0, x approaching 0 is right about here. Yeah, we can do that. Right? Literally, if I want to find out what's happening right here, let's just plug in the number 0. If I plug in 0 and put 0 right there, 1 over 0 minus 2 gives me -1/2. And as I approach from this side and as I approach from this side, I think either way, it's going to give me -0.5. I don't really need to test that out. But here's the whole example I've kind of been waiting for here. Again, on this graph that we have here, just drawing it one more time. Let's say we talk about when x is 2. Can you plug in 2 like I did with a 0? And you can't. I cannot plug in 2 because it's not valid, right? 1 over 0 would give you an error. But I can still talk about the limit, perhaps. What happens as we go along from the left-hand side? What is this getting closer and closer to? And if I were to write this out here, the limit as x is approaching 2 from the negative sign for our function, the answer is it's getting really close to -infinity. Because it just keeps going downwards, right? It's dropping straight downwards like a rock. And so the values keep getting lower and lower to the point where it's -100, -1,000,000, -1,billion. It keeps getting smaller. Well, let's approach it the other direction. Let's go backwards and let's approach 2 as an input value. But now let's approach it from the positive side. The limit now as x approaches 2 from the positive side, right here, is +infinity because it's going taller up here. Are these two things honing in on the same number? I mean, they can't hone in on 2 anyways because 2 doesn't exist, but were they approaching the same number in the same way that this graph right here? See how they're both still kind of meeting at the same location, even if the location is empty? And the answer here is no, they're not. So the answer for this one is, as the Mean Girls kind of thing goes, the limit does not exist. So if you've seen the movie, if not, it's getting to be a dated reference. It's like Lindsay Lohan way back in the day. So this would be a limit that does not exist. Okay, let's try some more. Right here, 1 over x squared. Now, maybe you don't know what these graphs happen to look like. An x squared graph would be your basic parabola. So if you do the reciprocal of that, it's going to do this. The red graph is going to be what it looks like. That should be 1 over x squared. And if you have to at first, please do not rely on your calculator. That is building such poor skills. But 1 over x squared, if you had to graph it, I should actually make it squared. 1 over x squared. Graphing looks kind of like this. It's almost like a volcano. It goes flat, hops all the way up, comes all the way back down. Now on this one right here, can you literally plug in 0? Can you do the first thing I want to do, or I just plug in 1 over 0? No, you can't, because the actual function does not exist there. But if I look at my graph and I look at a table of values, what's happening as we're approaching from both sides? Well, as I approach from the negative side, getting bigger, it's getting closer to positive infinity. And as I approach on the other side, it is getting closer to positive infinity. So on this one here, there is a limit. The limit is that it's approaching infinity. It's getting bigger and bigger on both sides. So that is our limit on this one here. Even though f of 0 is an error, and it is not a continuous function, there is still a limit though. Now sometimes this gets really confusing when you start talking about, let's put this absolute value graph in here. So sometimes the best way of doing this is, first of all, just try plugging f of 1 in. Well, I can't. If I plug that 1 in right there, it gives me 0 on the bottom. But I could plug f of 1.0001. Could plug that one in. So this would be fine. If I were to do 1.0001 minus 1 on the top, that would give me that. Now, if it was positive, it stays positive. So since it was positive, I'll keep it the same. And then I should be dividing by, 1.0001 minus 1 did the exact same thing on the bottom. Well, the limit from there looks like it's 1. Right? As it's approaching from the positive direction, it was 1. What about the negative direction, though? If we do the negative direction, 0.9999, let's talk about that. If I do 0.9999 minus 1, I should get a negative number on the top. However, that negative number on the top, using the absolute value signs, will become positive. So the top is actually still 1e to the minus 4. Right? However, on the bottom, The bottom of this fraction right here, when I type in 0.9999, when I type that in right there, the denominator of this fraction will be allowed to give me a negative number, right? It'll give me 0.9999 minus 1. And now when I do it, that limit's minus 1. What we've created a graph here is a graph where when you approach from one side, it gets closer to 1. I gotta do this properly though. On the bigger side, it gets close to the number 1. But as you approach on this side down here, it's actually at negative 1. And we're going to focus on some graphs that you're not familiar with, because this is not one that you probably have graphed before. But if you did want to use your graphing calculator, let's do it here. I'm going to do the absolute value. Hopefully you've seen how to do absolute value at some point before, of x minus 1. And then I'll divide by x minus 1. And I'll look at what this graph is here. Look at that graph. That's a crazy little graph. It goes flat one way, and then it just hops up here. Even look at the table of values. Look at this. I'm going to change my table from going up by 6s. Let's go 0, and I'll go up by 1s. So I don't want you to rely on this, but look. This is a graph that literally is negative 1 all the way across, gives you an error at 0, and then starts at positive 1. That's what the graph looks like. If I were to sketch this a little bit nicer, the graph looks like this. All the way across, no value here, hops right up to here, and goes across. That's what this graph looks like. Is there a limit? This side and this side, they don't approach the same value. Let's do another example here. Let's say we do a piecewise function. This piecewise function, I should sketch a quick graph to see what it looks like. It's x squared minus 2x plus 1 when x is greater than 1. So first I should figure out what that graph looks like. So that, if I figure it out, is going to be x minus 1, x minus 1. So that's going to give you an intercept at 1. And should look something like that. A double root at 1, looking something like this, which also makes sense because your y-intercept's at 1 right here. Then in red, I'll do the other one. This is 3 minus x. So this will be a y-intercept of 3, and then have a slope of minus 1. So it's going to go something like this. Okay, so there's our two graphs. However, this is a piecewise function. I only get portions of each one. So I get to have the red graph if x is greater than 1. And I believe 1 is going to be right there. So I get to have the red graph only if it's greater than 1. So there. And then I get the black graph only if it's less than 1. So less than 1 means we're only going to get this little bit right here. And it's going to have to be an open circle down here because we don't actually get that value. So maybe I'll clean this up a little bit. I'll get rid of that y-intercept here and draw it. You're going to have a part of a parabola that ends down there, and then it jumps up to being this graph right here. What happens as x approaches 1? Let's try it from both sides. As I approach from 1 from the negative side, I'm actually using this equation right here. If I try throwing in, like, say, 1 squared minus 2 by 1 plus 1 gives you 1 minus 2 plus 1 gives you a 0. Yeah, this side right here is 0. And, I mean, I plugged in 1 just because I could in this example here. If I try plugging in 1 right here, 3 minus 1 gives you 2. That means that this guy right here is getting close to 2. This one's getting close to 0. This one's getting to 2. Does the limit exist? It does not exist. So hopefully that made sense. Like I've been saying all along, make sure you give me a list of questions. And then whenever we get our face-to-face talking time, which ideally is Tuesdays and Thursdays during my office hours, but if that doesn't work for you, we have to do some email or we'll have to do whatever we can. Make sure you have a list of questions for me to try to be able to help you answer, okay? So, okay, we got one last example, then we'll call it a lesson here. Let's try this one. So, first thing I'm going to want to do is just get a quick sketch, a negative x cubed graph. Again, hopefully you have some knowledge about how this works. An x cubed graph normally would look like this. But if we want it to be a negative x cubed graph, it's going to look like this. And then for the other graph, it is x squared, x plus 2 squared, which should have an x-intercept of negative 2 doubled up, and so it should do something like this. The y-intercept of this graph, of this parabola, right there, 4, right? Because 2 squared is going to give you 4. That's your constant term. Now let's hack each half of the graph off here. So it's -1 that we have to remove. So -1, that might even be where they intersect. We're going to find that out when we test it in a bit here. So let's take this x cubed graph, and we only get it if it's less than -1. So I'm going to get rid of all of the larger side of the negative cubic graph. And then for this one here, you only get it when it's greater than 1. Greater than 1. Well, 1 itself is going to be right about there. It looks to me like we're going to have a graph where we're going to do something right here, open circle stop, and then we're going to re-pick it up over here at 1 and keep going. This is a strange graph. You probably aren't familiar with these, but I mean, this is a function. We can work with this. It doesn't break any function rules. There is a huge gap right in the middle of this thing here where for whatever reason there's no values. If I ask you what happens when x is 0, like if I ask you for f of x and I say what is it when x equals 0, the answer is you can't do it. Error, right? I'm not allowed to plug in 0 right here. It's not part of my domain. I'm not allowed to plug in 0 here. It's not part of my domain. It's been eliminated. So as I look at this graph then, if I approach -1, well, if I approach -1 from this side right here, yeah, look, it's getting close to a value, right? I can probably find that value. -1 cubed would give you -1, but there's a negative in front of it, so it's going to be +1. So it looks like it's getting close to 1. But as I approach from the other side, it doesn't even approach from the other side, right? Like it approaches all the way up to here, and then the graph stops. It doesn't keep going right there. So, I mean, on one side, the limit exists. On the other side, it doesn't exist. Like if I were to ask you the limit for this graph as x approaches -1 from the negative side, it looks like it's getting to be 1. But if I ask you to find this as it approaches -1 from the positive sign, that one on its own doesn't exist because it doesn't approach from the positive side. There is no graph there. So therefore, the limit as a whole for -1, without putting a little sign here, just the general limit of f of x. Since this one doesn't exist and this one is 1, they're not converging on the same spot. So that one's also a does not exist. Oh my goodness. D and E does not exist. Okay, so there's kind of my lesson. It's a strange concept, isn't it, this limit stuff? The idea basically being that we want to see what happens as it approaches, as it gets closer and closer from this side and this side. And if they're approaching the same value, that value itself may not even exist. But if they both approach the same number, then we have a limit. Okay? So think of a limit as what happens as you get closer and closer. So back to my wall concept of that one guy's paradox. As you get closer and closer to the wall, what are you getting? What are you approaching? Are you approaching 6 or 7 or 2? And if you're approaching from the other side of the wall at the exact same value, well, then there is actually a limit there. And if one side approaches at different spots, that doesn't work. I was just thinking, maybe use that wall analogy. Imagine there's a wall right here, and imagine that they want to break down the wall maybe. And so this guy right here, he's going to start drilling at a height of 5. And this guy right here, he can't see the other guy, right? He's going to start drilling at a height of 2. You know, they've communicated by messages over the walls, and they said, we're each going to start drilling from one side over the other, right? Will they actually meet up? Well, no. This guy's going to drill through to here, and this guy's going to drill through to here, and they're never actually going to meet up. So in that case, there is no limit. They're not meeting. But if they just so happen to make it so that this guy also drilled at, like, say, a height of 5, and this guy comes in at 5, and this guy comes in at 5, they could meet in the middle right there at 5, and then there would be a limit because it would match up. Right? Now, the function itself may or may not even have a point at 5. There could be like as you approach from one side and as you approach from another side, there could be a hole in the graph if it's a discontinuous function. But we're not sure. It really depends on the graph. So I showed you a couple of interesting graphs here, right? Here's a piecewise graph. Here was another piecewise graph. I'm betting that most of you have never worked with a with a rational absolute value graph. Like that was a really strange one, the one where it did this. Right? But that's the idea here, is we're going to start considering new and odd situations. So, okay, there's my lesson. Rewatch it if you need to. Email me questions if we can talk over Google Hangouts. Ask me questions. But you guys should now be able to begin the first little bit of your next assignment. Obviously, you'll want to watch the next couple of videos as well, but at some point, start looking at assignment 2. So, okay, I'll pause the video.